All right, so 11.2 vectors in the plane. All right, vectors are a little tricky. We're going back to basics physics here, and the thing I always remember is just break them into x's and y's if you have a tough problem. All right, and from there on, it's really not that hard. Uh, Notice the funky parentheses. That means it's a vector. This would mean a point. This is a vector. Okay, make sure we're clear about that. It's going to make your life a lot easier if you are. All right. So this is often in bold, by the way, sometimes a little hat on it. Be aware. All right. Find the magnitude and direction of this vector. So we actually use a coordinate plane to do that, and we almost always start at the origin. Over -1, up √3. So the vector looks something like this. We put a little hat on it, a little arrow on the end, and that's how we know it's a vector. We don't have to start at the origin, right? We don't have to draw the vector from the origin. Right? This is the same as this vector, is the same as this vector, is the same as this vector, as long as they're all pointing in the same direction and all have the same magnitude. How do we find magnitude? Well, how do we find the length of this? That's pretty straightforward. And I believe it's usually like this. Give me this value, which is square root of -1 squared plus √3 squared, which last I checked is 2. All right, well, how do we find the angle? Well, first off, and I'll leave it in degrees. It's 90 degrees, and then we go over here, and we know what this is. We'll go 180 minus this angle. All right, it's -1 √3. So it's arctangent. I'm going to get rid of the -1 of opposite over adjacent, which last I checked would give me 60 degrees. Yes, we could go in radians and all that. Therefore, theta equals 180 minus 60 equals 120 degrees. Right? Nothing too horrible. How often we have to do this in AP? Almost never. But it's good to be aware of what we're talking about with vectors. All right, put them in the coordinate plane, play with them from there. So how do we indicate the magnitude of a vector? I just showed it. So it's the absolute value thing. Might have units in here, be aware of that. All right, so, all right, let's go the other way. Find the component form of a vector with magnitude 3 and direction angle 40 degrees. So we always put it at the origin because it's easier. 3 would be almost a polar coordinate thing. 1, 2, 3, it goes out here. 40 degrees is a little bit less, something like that. This distance here is 3. All right. So, okay, well, how do we find them? That's easy. It's a cosine and sine. So what are we going to call this component form of a vector? We'll call it u. All right. I don't like giving it tail. U, because V's got the tail and U does not. Crisscross equals, all right, I'm not doing any math here. Cosine of 40 is adjacent. 3 cosine of 40 degrees. 3 sine of 40 degrees. That's it, we're done. That's breaking it into component form. All right, just a little bit of simple trig. All right, well, what's a scalar? Well, that's pretty straightforward. It's just some number, all right, that we're going to multiply by to bump it up. It's a constant, all right? How do we multiply by scalar? Well, if I have, say, -2 times that u we just did, it would be -6 cosine of 40 degrees, -6 sine of 40 degrees. And that's how you multiply by a scalar. You just slap it out front. So now we just get back into kind of physics, and this is the u vector, that's the v vector. Find 2u plus 3v, u minus v, and the absolute value, whatever. All right, so 2u equals -2 comma 6. That's it. I'll keep this going. 3v equals 1221. 2u plus 3v equals 1027. All right, that's about it. U minus v equals -1 minus 4, -5. 3 minus 7, -4. Okay, and 1/2 u equals -1/2, 3/2. And absolute value, in other words, the magnitude, is square root of 1/4 plus 9/4 is 10/4 equals square root of 10/2. Notice I could have just done this. I get square root of 10 and then multiply by 1/2. Either way is going to work. Now we can actually do some problems. And like I said, when I get these big nasty problems, I just break them into X's and Y's and go from there. So airplane flies due east at 500 miles per hour in still air. Yeah, right. For those who don't know their directions, that's 500 miles per hour due east. Suddenly it encounters a 70 mile per hour tailwind acting in the direction 60 degrees north of east. So this is east, this is north. Suddenly gets a vector here, way too big, 70. And this is 60 degrees. All right, what's its new speed? What is its heading and all that nonsense? Well, it's going 500 miles an hour. It's easy. It's just one vector. So let's just say that this vector is 500 in the x, comma 0. I'll call it original speed. The wind is, we break it into x's and y's, 70 cosine of 60, 70 sine of 60. All right, new speed. Let's see, cosine of 60, 1/2. 1/2 of 70, 35. 535 miles per hour. And 70 sine of 60 is root 3 over 2 is 35 root 3 plus 0. So there's our new vector, which is completely useless to an airline pilot who wants to know how fast they're actually going and in what direction they've been pushed. So we get this fun stuff, square root of 535 squared plus 35 root 3 squared. Plus that all out. I've got an answer in front of me, but it's not rounded properly, so I want to do this right. $538.424 miles per hour. All right, so what's this new direction? Well, we use this vector here. We say theta equals arctan opposite 35 root 3 over 535. Now I'm going to make sure my calculator is in degrees for the first time ever. second tangent, 35 root 3 divided by 535, 6.465 degrees. And that would be north of east. You can see if you look here, it's getting knocked around. Its new path is like that. Classic physics. Will you see this on an AP test? Nope. Just giving you practice. Would you see on one of my tests? Possibly. All right. So other ways to mess with vectors. Really, we're just playing with the x and y's. Not all that hard. A particle moves in a plane, so its position at any time is blah, 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 blah. Find position, vector, velocity, vector, acceleration, vector. So this bothers me. Probably should have parentheses, the funky brackets. All right. Not that big a deal. But its position vector is r of t, s of t, could be anything. I decided to go with r of t. Sine of t, t squared over 2. How about velocity? Well, we just take our derivative separately. 2t over 2, t's cancel. How about acceleration? Negative sine of t, 1. All right. What's going on at t equals 6? Well, at t equals 6, the position vector is sine of 6, whatever that gives us, 18, and we'd get back into radians for this. Velocity vector gives us cosine of 6, 6. And the acceleration vector gives us negative sine of 6, 1. Right? Just blasting it out. Let's do one more here. I should probably have deleted one of these, but what are you gonna do? I did delete. I did a couple of these. That's funny. Particle moves in an elliptical path so that its position at any given time is given by this vector. By the velocity acceleration vectors, find out what's going on at pi over 4 and sketch the path of the particle. Blah. By the way, you can always put this into your calculator mode. I'm going to put radians on just because I always want to be parametric. And then you go up here to y equals, and you can see, you can't see. There you can put in parametric, and you can see that it's got an x and y function. But we're going to skip that. We'll see what we can do without it. All right, let's start with this one. Again, this should have brackets. V of t is for cosine of t, negative 2 sine of t. A of t, negative 4 sine of t, negative 2 cosine of t. All right, what's the velocity? Pi over 4. 2 root 2. By the way, I've been noticing I tend to forget to make my funky brackets because it's just not natural. So try and stay on top of it. It's hard. And negative root 2. Because cosine of pi over 4 is root 2 over 2, and so is sine of pi over 4. Acceleration is negative 2 root 2, negative root 2. Notice that the velocity acceleration are the same. Well, that's just at a point in time. Really doesn't matter. Okay, so sketch the path. Well, we need the original. I happen to know that this is a parametric because I would go with x equals 4 sine of t, x over 4 equals sine of t. And then I would go with y equals 2 cosine of t, y over 2 equals cosine of t. Square them out together, and I would get x squared over 16 plus y squared over 4 equals 1. I happen to know that is a ellipse. It starts out here at 4, I believe. Goes up as high as 2. We're probably saying, I thought we already did parametric. Why are we doing parametric? Yeah, vectors are just a form parametric. It's defining with, x is a t and y is a t. They're parameters t, and off you go. Plug in 0, 0, 2. Looks like it starts up here. Interesting. I believe I have it wrong in my previous notes. That's fascinating. So I believe it starts here. Starting point. And let's see what happens when I plug in pi over 2. So 4 sine of pi over 2, 1, 4. So now it's at 4. And then 0. So it looks like it's going this direction. All right. Looks like it travels counterclockwise around the origin. All right. Cool math. All right. I got to be honest. I find this a little bit challenging. It's one more step from, all right, I'm kind of getting this. And then you hit me with this nasty stuff, and I get a little bit lost. So we'll see how it goes. How do we find displacement and distance traveled? Displacement's the same. Displacement from A to B of particle velocity is right here. Integrate separately. All right. So displacement means on a number line, I start, who knows where? Here's 0, but I start at 2, and I go here, and I come back to 3. That's my displacement, 1. That's not how far I traveled, but that's my displacement. What my position is would be a better way to put it. All right, so we integrate them separately. All right, great. Then how do I find the distance? Oh, it's another one of those weird things. The distance traveled is the integral of the absolute value. Integral of velocity squared plus velocity squared. That's distance, so check it out. Should have emphasized it up here. We're integrating velocity to get to position. If we're given position, we just use position, all right? But in this case, we're given velocity. All right, so distance traveled is absolute value, but look at it's just a little bit different. This is our third formula we have to remember. We've got a big square root of something squared plus something squared. The first one is length of a curve in dy dx. It was from A to B, 1 plus dy dx squared. All right, so we did that one. And then we had parametric. Actually, it's the second one already. Well, no, parametric's a little bit different, but it's the same idea. Parametric was this one, where the length of the curve is from some L1 to L2. And it was dx dt plus dy dt. This is more or less the same thing. All right. Integral of velocity, velocity is dx dt, dy dt. It's more or less the same thing. So if you can remember this, you should be able to remember that. All right. One more time. All right. Particle moves with a velocity vector in a plane, particle at the point, find the position of the particle at t equals 4. Starts at 1, 5. Is that important? Really shouldn't be. No, I don't think so. So find the position at t equals 4. Well, if I recall, integral 0 to 4, t minus 3 pi cosine of pi t. No squared in here. Very tempting. Integral 0 to 4. 2t minus pi sine of pi t dt. Gives us a shockingly simple answer, 8,16. Now, this is annoying. That's displacement. I'm wrong up here. I'm not wrong. This equals 1. Started at 2, ended up at 3. That's displacement. Well, what's the position? Position was 2, and now it's 3. What's the position? Well, it was 1 comma 5. Notice I've got parentheses. Ends up at 9 comma 21. Told you I don't like this. It's a little confusing. It's not the end of the world, but it's a little confusing. So, all right. You're going to have to bang it out. I could sit here and go over it for another 2 or 3 hours until you do problems. It's just not going to happen. All right. Total distance traveled. I don't care where it started. I don't care where it ends. The total distance traveled. Integrals on the outside, 0 to 4. Big honking square root. B minus 3 pi cosine of pi t quantity squared plus, you think this might be a calculator problem? I think there's an outside chance. 2t minus pi sine of pi t squared dt. I'm gonna be honest, I don't remember doing this. I don't remember like, oh yeah, this all makes sense to me from years past. This is a distance, so meters, inches, miles, whatever. What does the path of the particle look like? Well, I was actually just looking at my calculator. It doesn't really show up very well. So I will just show you. It does some very, very bizarre thing. All right, since it's in X and Y's, it starts here and then it curves and then it goes up here and then, yeah, if you want to graph that on your calculator, I highly recommend it. Put it in radians, put it in, let's make it a show this time. Mode, helps if it's on, mode, put it in parametric and graph that sucker. See what happens. That's a lot. Good luck.